Sometimes it feels like you're just drowning in information,
Yeah.
right? Especially with tech stuff that changes so fast.
Oh, absolutely.
You really want to get to the core of something complex, but wading through endless articles and docs,
Yeah.
it can be overwhelming. How do you even start to cut through that noise?
It's a real challenge. The aim isn't just gathering facts, it's genuine understanding, connecting those dots, and doing it efficiently. Ability. Pick the best tool for each specific job.
Okay, so that contrast with the older ways, the monoliths, seems pretty stark. Can we dig into that difference a bit more? Why the big shift?
Sure. So in a traditional monolith, everything's bundled together. All the features, all the code, deployed as one single unit.
One big package.
Right. Need to update just one tiny part. Often you have to rebuild and redeploy the entire thing. It's quite rigid.
Painful.
It can be. With microservices, like we said, each piece is separate, self-contained, deployable on its own schedule.
It's like that comparison. An ocean liner versus a fleet of smaller boats.
Yeah, I like that one too.
If the liner needs repairs, the whole ship docks. Everything stops.
Mm-hmm.
But with the fleet, our microservices, one boat needs fixing. You just pull that one boat out,
Yeah,
the rest keep going.
exactly. So monoliths deploy all at once, scale as one block, often mean one big team, and usually lock you into one technology stack.
Whereas microservices,
Hmm.
you deploy individually, you scale per service. That's huge.
Crucial difference.
You can have smaller, focused teams working in parallel. And you mentioned polyglot persistence.
Yeah.
Bit of jargon there.
Yeah. It just means different services can use different types of databases, if it makes sense. One might use a relational database, another a NoSQL one, whatever fits the specific need best.
That flexibility sounds great, but I can already hear people thinking, doesn't mixing all those technologies create its own headaches, management complexity, security risks?
That's a really sharp question. And yes, it absolutely does introduce new kinds of challenges, different ones. But there are patterns and tools to manage them, which we'll get into.
Okay.
But first, let's stick with the basics. You've got these independent services.
Yeah?
They have to talk to each other somehow. How does that communication actually work?
Right, how do they coordinate?
Typically, they use lightweight protocols. HTTP with REST APIs is super common for simple request response stuff.
Yeah.
Or maybe gRPC if you need higher performance. There's also asynchronous communication using message queues.
Like RabbitMQ or Kafka.
Exactly. Those act as brokers, passing messages between services without them needing to talk directly in real time.
So you have two main styles.
Oh.
Synchronous, like a direct call.
Uh-huh. Request and immediate response, like making a phone call for info you need right now.
And asynchronous, where you send a message and it gets processed later.
Right, more like sending an email or a memo. The sender doesn't wait. It's often better for decoupling services and improving resilience.
Makes sense. So direct calls tie services together tightly, while messages let them operate more independently.
Precisely. And you'll often see API gateways used too.
Ah, the gatekeeper.
Kind of, yeah. A central point that routes external requests to the right internal service. It can also handle things like authentication, rate limiting, sort of a front door.
And for reliability between services, things must fail sometimes.
They do. So you need strategies like automatic retries for failed calls, setting timeouts so services don't wait forever, and having fallbacks, graceful ways to handle things if a service isn't available.
Okay, that leads nicely into another big challenge. Data. If each service potentially has its own database, how do you keep data consistent across them all?
Ah, yes. The data consistency conundrum. Maintaining that strong, immediate consistency you get in a monolith across distributed services is, well, it's incredibly hard.
Almost impossible without killing performance.
Pretty much. So the common approach, and it sometimes surprises people, is to embrace something called eventual consistency.
Eventual consistency, meaning things will become consistent eventually.
Exactly. The data across different services will sync up, but not necessarily instantaneously. There might be a small delay.
Like your bank branch example. A transaction posts here instantly, but takes moments to show up everywhere globally.
Perfect analogy. Over a short time, they all reconcile to the same correct state. It's a trade-off you make for the benefits of distribution.
So how do you manage that journey to consistency? You can't just hope for the best.
Definitely not. You use specific patterns. The Saga pattern is a big one.
Sagas.
It orchestrates a sequence of local transactions across different services using events. If one step fails, there are compensating actions to undo the previous steps.
So ways to roll back cleanly if a multi-part operation goes wrong.
Exactly. You also use compensating transactions directly and design operations to be idempotent.
Idempotent meaning you can run it multiple times without messing things up.
Correct. Repeating the operation has the same result as running it once. Essential for reliability when messages might get redelivered. And tools are critical here, Kafka, for streaming events between services, Debezium for change data capture.
Capturing database changes and streaming them.
Yeah, effectively turning your database changes into an event stream that other services can react to. It's a powerful way to achieve that eventual consistency.
Okay, so microservices offer big advantages, but they definitely bring new complexities. What are some other common hurdles, and crucially, how do teams solve them?
Good question. Well, with potentially hundreds of services, just finding the right service to talk to can be a problem. That's called service discovery.
How do they find each other?
Tools like Netflix Eureka, HashiCorp Console, or even just the built-in service discovery in Kubernetes handle this. They maintain a registry of available services and their locations.
Okay, discovery solved. What else? Tracking what's going on across all these moving parts must be tough.
Oh, incredibly tough. Monitoring and centralized logging are absolutely non-negotiable.
You need to see the whole picture.
Exactly. You need tools to aggregate logs from all services into one place. Think the ELK stack. Elasticsearch, Logstash, Kibana.
Right.
And for metrics, CPU, memory, request latency, things like Prometheus and Grafana are standard. Plus, distributed tracing with tools like Jaeger lets you follow a single request as it hops between multiple services.
Essential for debugging.
Absolutely essential.
Wow.
Then there's fault tolerance. This is a big one.
Meaning if one service fails, it doesn't bring down the whole system.
Precisely. You don't want cascading failures. Patterns like the circuit breaker are key here.
Like an electrical circuit breaker.
Very similar idea. If a service starts failing repeatedly, the circuit breaker trips and stops sending requests to it for a while, preventing a domino effect. Tools like Resilience 4J or the older Hystrix implement this.
It really does sound like managing a complex system, like that airport analogy. Control towers, radar, emergency plans.
It's a good way to think about it. And yes, just managing the deployment of all these separate things is complex too. That's where CI/CD pipelines and container orchestration really save the day.
CI/CD, continuous integration, continuous delivery, automating the build, test, deploy process.
Right. And platforms like Kubernetes manage the containers holding your services.
Which brings us neatly to deployment and scaling. How do you deploy and scale effectively? You mentioned containers in Kubernetes.
Yeah, that's pretty much the standard way now. You package each microservice into a container. Docker is the most common format.
Sure.
Then you use an orchestrator, usually Kubernetes, to manage deploying, running, and scaling those containers across your servers.
And the beauty is scaling just one service.
Exactly. Back to your supermarket example.
Right. Busy frozen food aisle doesn't mean opening a whole new store, just more checkouts.
Perfect. Kubernetes lets you scale only the services that need more resources, often automatically using something called horizontal pod autoscaling. It watches CPU usage or other metrics and adds or removes container instances as needed.
Efficient. And how do you release new versions without downtime?
Several strategies. Rolling updates are common, gradually replacing old instances with new ones. Or blue-green deployments.
Blue Cream.
You have two identical environments, blue running the current version, green running the new one. Once green is tested, you just switch the router to send all traffic to green. Instant switchover, zero downtime. If something goes wrong, you can switch back just as quickly.
Clever. Okay, last major area. Security. Seems like having all these distributed services creates a much larger attack surface.
It definitely does. Security becomes more complex, arguably more critical. You have many more network endpoints and internal communication paths to secure.
So what are the key practices?
It starts at the edge, often with the API gateway we mentioned.
The gatekeeper again.
Right. It handles centralized authentication, verifying who the user is, and authorization, checking what they're allowed to do. Plus, rate limiting to prevent abuse.
Okay, so that secures the front door. What about inside? Users and internal communication.
For user identity, you rely on standards like OAuth2 or OpenID Connect, often using JSON Web Tokens or JWTs. These are like secure digital ID cards.
Got it. And service-to-service calls. How do services trust each other?
That's where mutual TLS, MTLS, comes in. It ensures that both services in a communication verify each other's identity using certificates, and the communication itself is encrypted.
So secure, verified links between services.
Exactly. This is often managed by a service mesh like Istio or Linkerd. The mesh sits alongside your services and handles all that complex network security automatically.
Wow, okay. A mesh handling the internal security fabric.
Yeah, it simplifies things significantly for the application developers. And underpinning a lot of modern security thinking is the zero trust principle.
Zero trust. Assume nothing is safe.
Basically, yes, don't automatically trust anything, even if it's inside your own network. Verify every interaction, require authentication and authorization for all calls, internal or external. It's a fundamental shift from the old trust but verify model inside the perimeter.
That makes a lot of sense in such a distributed world. Wow, okay. Yeah. We've covered a lot of ground there.
We really have. A comprehensive journey through microservices, hitting those 7 key questions.
Yeah, we started with the basics, what they are. Then that crucial contrast with monoliths.
Highlighting that fundamental shift, yeah.
Then we look at how they communicate sync, async, APIs, queues.
Right, and different patterns and protocols.
Tackled that thorny issue of data consistency, embracing eventual consistency and patterns like sagas.
A really important concept to grasp.
Then the common challenges, discovery, monitoring, fault tolerance, and crucially, the solutions.
Because the solutions exist, they're mature now.
Then we dove into deployment and scaling containers, Kubernetes, auto-scaling, zero downtime releases.
The operational side, which is vital.
And finally wrapped up with security, API gateways, MTLS, service meshes, zero trust.
Layering those defenses in a distributed environment.
So hopefully this deep dive is giving you, our listener, a really solid understanding of this critical architectural style.
Yeah, a well-informed perspective, some practical insights, maybe even an appreciation for the elegance and complexity involved.
Definitely. The elegance and the complexity of distributed systems.
And maybe, thinking bigger picture for a moment, this whole idea of breaking down a massive, complex problem into smaller, independent parts that communicate clearly.
That's a powerful principle in itself, isn't it? Beyond just software.
Absolutely. Which kind of leads to a final thought for you to ponder. Where